Hi everyone, this is Rui-Xiao and I'm glad to give a presentation about our work which is called Enhancing the Resource Management of the World's Largest PCDN System for On-Demand Video Streaming. As denoted by a recent report, on-demand video streaming plays a dominant part of the downstream volume, which takes about 54% of the overall traffic. At the same time, such a high bandwidth cost can give a great burden to content providers. As reported, for Kuaishou, one of the major content providers in China, its bandwidth expenses are the highest operational cost except for revenue sharing, marketing expenses, and employee benefit expenses. Therefore, how to reduce bandwidth costs is a critical problem for the content providers. Currently, CDN is the most popular tool used for video delivery. That is, ByteDance will rent multiple CDN providers and pay for the bandwidth. To save the bandwidth costs, starting in 2020, ByteDance began exploring the use of edge nodes as a partial replacement for CDN. Different from CDNs, which are usually server clusters, the edge nodes we use are mainly composed of idle computing resources on the internet. For example, smart home devices and outdated servers. And they are collected by the third-party companies and sold in bundles to us at a heavily discounted price compared to CDNs. And usually its bandwidth price is just the half of the CDN's price. Moreover, these edge resources are crowdsourced in China. In our system, there are over 1 million nodes located in more than 200 cities. However, some features of these edge resources make them difficult to be directly utilized to replace CDN. First is the heterogeneity. We measure the maximal bandwidth of all the edge nodes and show their distribution. We can see that the maximal bandwidth varies significantly. And at the same time, we can see that the majority of these nodes are the small ones. Second is the poor performance. For download speed, we can see that over 80% of the nodes have speed less than 5 megabits per second. In contrast, the average speed for CDN in our system is usually more than 24 megabits per second. Moreover, due to the network address translation, some nodes may not be accessible. Different from CDN clusters with public IP addresses, the edge nodes are probably behind net. We measure the number of different net resources and also their connection failure rate. We can see that there exist over 23% of non-public IP nodes and their failure rate is more than 60%. To leverage the potential and overcome their disadvantages, ByteDance has developed a customized edge-based delivery system called PCDN. The core idea of PCDN is to use multi-cells parallel downloading. That is, unlike CDN, which serve users with only one server, the user in PCDN will simultaneously download data from multiple edge nodes. In detail, PCDN is composed with both server-side and client-side. We also present the typical workflow. That is, the video player will first initiate a downloading request, and then the tracker service will be invoked, and then determine which node should be returned to the client. After obtaining the nodes, the client will start downloading data in a multi-source way. However, after a long time operation, we find that our PCDN system suffers some unbalanced resource utilization problem. We can see that over 22% of the nodes are already overloaded, while 30% of the nodes are still underutilized. At the same time, this unbalanced problem is mainly from bandwidth instead of CPU utilization. Actually, this unbalanced utilization can further introduce two critical problems. The first is that the overloading can decrease the service performance. We can see that there will be a significant speed decrease when the node serving too many viewers. Second, we also find that low-priced resources are more likely to be underutilized. We present the bandwidth utilization of different priced resources in the bottom subfigure. We can see that the bandwidth utilization for the low-price resources is significantly lower than other resources. To solve these problems, we conduct large-scale measurement studies. We first investigate the server-side logic, and it determines which nodes should be returned to the user. We find that the server-side decision is highly skewed. That is, it tends to return a small number of resources. So for illustration, we sort all nodes in descending order based on their return frequency. We can see that the top 10% of the nodes have been returned in 32% of the requests. Second, we find that service speed can also be influenced by a lot of factors, but PCDN selects nodes only based on some fixed rules. Here we show an example. We present the download speed for different providers and regions, and we can see that their performance varies significantly and the difference is not consistent. Therefore, we can conclude that PCDN server-side decisions are static and lack of a global view. Second, we also measure some thing in the PCDN client side. PCDN client side download data in a free competition way. That is, it starts downloading data as long as a connection is established and sends the data request whenever there is a free congestion window. However, in the multi-source downloading scenario, such an approach can introduce randomness in the resource consumption. Here, we give an example. We repeatedly download the same video file from 3 identical nodes, and we then analyze the speed contribution for each of them. We can see that the speed contribution of each node varies significantly. Take node A as an example. Its highest contribution is about 25 megabits per second, but the lowest speed contribution is even less than 0.4 megabits per second. This lack of control on the client side prevents it from achieving on-demand resource allocation, therefore cannot coordinate with the centralized logic. So to solve these problems, we evolved previous PCDN to PCDN Plus. The basic idea of PCDN Plus is to augment previous PCDN with a centralized logic on the server side and a decentralized logic on the client side. And the server side will not only determine which nodes should be returned, but also determine how much contribution each type of node should make in the downloading task. And this decision is denoted as decentralized decision. The decentralized logic will help PCDN Plus to achieve the on-demand resource allocation. And through this design, PCDN Plus is both a dynamic and also a controlled system. To achieve the goal for the centralized logic, we design it with a profiling optimization framework. The profiling stage will characterize the download speed when assigning different featured users and edge nodes. And after getting these characteristics, we then model the allocation process as the optimization problem. Profiling stage will divide users and nodes into groups based on some pre-selected features, and these features are selected based on 2 criteria. The first is that the users and the resources in the same group should be similar. This is because if there is a significant speed disparity within the same group, the resources will be mistakenly allocated. And second, that the feature number cannot be too large. This is because to ensure the fast connection establishment between the node and the viewers, we have to transmit all necessary information in a single MTU packet. And because some metadata information has already occupied a significant portion of the packet payload, so we cannot include so many features. So after some feature engineering, we finally select the following features. Currently, we use this static feature selection, and we plan to use some dynamic feature selection in the future work. After profiling stage, we further step into the optimization stage, and here is a formulation. The meaning of this is to find an allocation which can minimize the bandwidth cost under some systematic constraints. And the objective function means that we want to minimize bandwidth cost. And the constraints means we should consider bandwidth limit and also the speed requirement. And the output of the optimization problem is the target contribution for each type of nodes for each type of users. And after solving this optimization problem, the server side will sort all the nodes according to the results and return both the decision, the output, and also the top-ranked nodes to the client side. In summary, we implement a profiling module and an allocation module in the PCDN Plus server side. And here we show the structure and its workflow. So let's come to the decentralized logic. So for each user, after obtaining the centralized decision and also the return nodes, the decentralized logic should help to achieve the centralized decision. Therefore, it should support the following two functionalities. That is, achieve on-demand resource allocation and also satisfy the speed requirement. And our idea to achieve these goals is to interact with the transport layer and enable some dynamic resource optimization. First, we show how we achieve on-demand bandwidth allocation. The idea is that we control the download bandwidth of each connection by setting a maximum congestion window, which controls the upper bound of the in-flight packets. And if a connection's bandwidth exceeds the target, we reduce its maximum window. And if it's below the target, we will increase it. This helps us to adjust bandwidth contribution as we want it. For example, we have 3 nodes in 3 groups as A, B, and C. Our goal for group A is denoted as heteXA, and we will monitor the total bandwidth and the contribution of node A, and we denote the real contribution as XA. And if we find that XA is lower than heteXA, we will increase its bandwidth share in the next round, and if it is higher, we will decrease it. We use a factor alpha to adjust the share. If we need to increase the share, the alpha will be larger than 1, and if we need to decrease the share, the alpha will be smaller than 1. And the next round bandwidth of the node A will be updated as this normalized equation. And finally, the maximum window of node A will be calculated as this bandwidth times RTT. Second, since we limit the maximum congestion window, we need to make sure that this operation will not have some bad impact on the speed. So the idea is that we divide the downloading scenarios into 2 cases based on where the bottleneck is. In the first case, that is, the bottleneck is located on the user side. In this case, we can safely change resource allocation without any impact on the performance. While for the second case, the bottleneck is on the node side. In this case, if too many data requests are allocated to the resource which are not sufficient to serve these requests, the performance will be decreased. So in this case, we need to dynamically replace the least performant nodes with performant ones. And through this design, the second case will be transferred into the first case, and we can safely change the resource allocation. Finally, we implement our design by introducing 3 modules in the PCDN client side. And that is a monitoring module, which is used for monitor the transport layer metrics such as RTT, loss, and bandwidth. And the control module, which is used to calculate the maximum congestion window, and also the optimization module, which is used to dynamically replace the unsatisfactory nodes. So finally, we conduct some large-scale A/B tests to demonstrate that our system is effective. And we start with evaluate the decentralized logic. We first compare the controllability through a metric called control error. And this arrow indicates that the distance between the achieved resource allocation and also the target one. And we can see that PCDN cannot achieve resource controllability because we can find that there is a huge control error. And while PCDN Plus performs quite well. Second, we also compare the download speed of PCDN and also the PCDN Plus. We can see that by introducing this controllability, we do not have any negative impact on the download speed. And we can see that the PCDN Plus has a competitive speed as PCDN. And third, we further do some ablation study to demonstrate that the optimization module for the PCDN Plus is very necessary. After testing the decentralized logic of PCDN Plus, we further conduct some experiment to evaluate the overall system. That is, we will evaluate PCDN Plus as an overall system. We first evaluate the resource utilization. And we can find that through PCDN Plus, the resource unbalanced problem has been well resolved. This is because our system is controlled and also supports dynamic control. Second, we also investigate the bandwidth costs. We can see that the workload of the low price resources for the PCDN Plus is significantly improved. And finally, we also compare the download speed. And we can see that PCDN Plus also performs better than PCDN. Here, I like to summarize this work. We first give a basic introduction to PCDN, which is the ByteDance edge-based delivery system. And second, we present the unbalanced resource utilization problem, which is caused by PCDN's static server-side decisions and also the uncontrolled client-side decisions. And after that, to solve the above problems, we then propose PCDN Plus, the next iteration of PCDN, in which we integrate the PCDN with a centralized logic and a decentralized logic. Finally, we do some real-world A/B tests to demonstrate that PCDN Plus effectively resolve the resource unbalance problem and also achieve both cost efficiency and higher speed. That's all. Thank you.